Now we introduce two more new functions which we already discussed in 11th standard in supplementary material, but let me just recap. The one that is called exponential and the other one that's called logarithmic, our standard log function. So a function, let me write from real numbers to r plus means positive real number, defined in this way: fx equals to a raised to x, where what is a? That is any positive real number, normally not 1, other than 1, and x is a variable. So this is a function of the type constant raised to variable, this type of a function. This is a constant and here it a variable. What is that constant? It is positive real number but should not be 1. If it is 1, then you know this become constant. 1 raised to anything is 1, that's why. So function defined in this way, a raised to x, is called exponential function. Is called exponential function. Constant raised to variable. Here a is called base sometimes. A is base and x, that's exponent or power, you know. Power or exponent. That's why this is called exponential function. Like this. For example, if I take fx equals to 2 raised to x, so I've taken a equals to 2, 3 raised to x, 7 raised to x, 1 by 2 raised to x, so a is 1 by 2, 1 by 3 raised to x, 10 raised to x. These all are examples of exponential functions. These are all exponential functions. Constant raised to variable, remember. Constant variable, not like this. If I write this, here variable and then constant, so you know that this is polynomial or quadratic. So this is not exponential. You must see the difference between these and this. Here you have variable raised to constant, here constant raised to variable, so this is exponential. You please see the difference between these two carefully. This is quadratic, this is exponential. Okay, now for any exponential function, whether it is 2 raised to x, 3 raised to x or 10 raised to x, for every x belongs to R, you can see that the range, chapter number 1, range of a function, RF, it would be always positive real number only, remember. You put 2 raised to 0, 1, 2 raised to 1, 2, for any number you can note this much. Try to find the range. It would be R plus, even 0 will not come. And that is same as codomain. You look at what was codomain of this function. It was also R plus. So this is onto. This is onto function. You know, range of the function equals to codomain, then it's called onto function. Not only that, if you take different x1 and x2, for any exponential function, their images would be different. You can just verify. So it means that exponential function is 1, 1. So it's 1, 1 and on to both. So it's bijective. On to 1, 1. So every exponential function from R to R plus is always bijective. And you know, chapter number 1 says, if function is bijective, then it must have an inverse. Right? That you know. So inverse of exponential exists. Inverse of exponential function from R to R plus exists. And is called, that inverse is called log function. Is called logarithmic function. That is simply log function. Okay. So what is log? So therefore log is a function from logarithmic. you know, here f is a function from a to b, then its inverse, that's a log function. It would be a function from b to a, so r plus 2r, codomain to domain, that you know, chapter number 1. R plus 2r defined as I'll write y equals to exponential a raised to x. Right? Log comes from exponential. You know, in inverse, if you have y is equal to fx, then you can find x equals to fy. That's called inverse. If and only if. So this is now definition of log function. So inverse means what? Change of variable. You express x in terms of y. So x equals to log variable y to the base a. This way we define. So this is very important definition. Remember. What is this? Indirectly you can say that there is a relation between exponential and logarithmic. If you have exponential, you can convert into log. How do we read this? Log y to the base a. Remember, base can be, this is the base of the log function. Base can be, go back to beginning, base can be any positive real number other than 1. Base can be 2, base can be 3, base can be 4, base can be 10, and so on. So this is a relation. I repeat one more time. What is this? Y equals to a raised to x if and only if x equals to log y, little below we write the base, that is base a. How do we read this? Log y to the base a. I repeat, log y to the base a. Remember, this is like y is equal to fx, and this is like x equals to f inverse y. This is function, this is the thing inverse. Now you have studied concept of inverse of a function and even inverse trig also, so this won't be difficult for you. Remember, exponential can be expressed in form of logarithmic and reverse. If you drop the log, you will get exponential. Right? Both are internally connected. If you have exponential, this is exponential. If I drop exponential, I'll get log. If I drop log, I'll get the exponential. Okay, now, so for example, if I take y equals to 10 raised to x, if and only if x equals to log y to the base 10. So this is sometimes called common logarithmic. Common logarithmic. The log table which are available in the market are prepared based on this log to the base 10. If I have this y equals to e raised to x, this is also an exponential function. What is e here? E is a constant which is same as pi. Remember, its approximate value is 2.71. What is e? E is a constant with approximate value 2.71. It's an irrational number like pi. Remember, pi is also irrational number. Pi is 3.14. Here it is 2.71. So how do I express in form of log? X equals to log y to the base e. This is sometimes written as ln y. You might have come across in physics. Ln y is just a log, but the base is e. Remember, we normally never use ln here. We use log. We write base e here. We write base 10 here. This is sometimes called natural logarithmic. Natural logarithmic. So these are the commonly used log. One to the base 10, the other one that is base e. Base e is sometimes also denoted by ln, and this is log. Okay, so this is just about definitions. Now I want to see the properties of specially log function. Some of them might be known to you. I'll list again here. Properties of log function. Under any base, this properties holds true. Remember, base is not important. Whether base is e or 10 or any other. The first property, let me write here. all this comes from the exponential function. Log 1 to any base a is always, look at this, you just write a raised to 0. You know anything raised to 0 is 1. So this is like y, and this is like a raised to x. Now express in form of log here. So we'll get the log y means 1, to the base a equals to 0. So what I have shown, log 1 is 0. So log to any base is always 0. Remember, base is not important. If I have log to the base 10, 1 is 0. If I have log 1 to the base e, again 0. Value of log function at 1 is 0, remember. Second one, log a to the base a. Let's see this. Now again, let me write like this. A raised to 1, you know it is a. This is exponential. This is like y, here a, and this is x equals to 1. So if and only if, now I'm expressing in form of log function. So log y means a, to the base a equals to here x. What is x? That is 1. So what I have shown, log a to the base a is 1, remember. If these two numbers are equal, value of the log function is here 1. So if you see the log table available in the market, log to the base 10 at 10 is 1. You might be knowing ln e is also 1. Why? Because ln means log e to the base e is always 1. If these two are equal, value is 1. If I have log 2 to the base 2, it is 1. If I have log 3 to the base 3, again 1, and so on. So these are the two important properties. One is log 1 is always 0, log a to the base a is always 1. We go to third property now. Next, log of x into y to base a, that is log x plus log y. This is one of the most useful property of the log function, that multiplication becomes addition. If you apply log inside the multiplication, becomes addition, remember. Under any base, this is always true. Fourth one, that is if you have division to any base a, then it becomes subtraction. So log x to the base a minus log y to the base a. Division becomes subtraction and addition becomes multiplication. Fifth one, if you have log of x raised to n, this is a constant, power of the variable, then here it would be n into log x. That power will be in the product, like this. For example, if I have log of x raised to 7, then it is as good as 7 into log x. So power will be in the product. If I have log of x raised to, let me write 2, then this is 2 into log x. Under any base, this all holds true. So I'm not writing base here, but base can be any, remember. Under any base, this is true. So these are again very important properties. Addition, multiplication to addition, division to subtraction, and power will be in the product. Sixth one, that is change of base. You can change the base, change of base. You might have done in physics also. So for example, I want to write from base A to B. From base A to base B. So if I have log x to the base A, I want to convert into B. So this is equals to, it says that the log, now base is B here. So base B here. Now this number, upper number you write in the numerator, lower number you write in the denominator. This is a change of base. Log x to the base A is log x to new base B, log A to new base B. For example, suppose I have log, let me write 2 to the base 10 and I want to convert in e. So I can write here log 2 upper number to the base e, log 10 to the base e. One more, suppose I have log, let me write for example I have here 5 to the base say e and I want to convert into 10. So log 5 to the base 10 and log e to the base 10, new base, upper number in the numerator, lower number in the denominator, write the new base. And from this we have one more property, that is if I have log x to the base a, if you take reciprocal then the base and number get interchanged. So log a to the base x. If you take the reciprocal of this expression, base and number get interchanged. For example, if I have 10 to the base e, if I take the reciprocal, it is 1 upon e to the base 10. If I have log 2 to the base, for example, say 10, if I take the reciprocal, 1 upon log 10 to the base 2. Right? If you take the reciprocal of the log function, these two will get interchanged. Okay. Next property, you know that if I take exponential and the other one is log x to the base a, this is like f and this is like f inverse. Log is inverse of exponential. So if I compose these two, I must get identity, you know. Identity means x itself, that you know. F OF inverse is identity, F inverse OF identity. So I'm just combining these two. So log of exponential a raised to x to the base a is again identity, that is x. This is like f inverse, this is like f. Composition of inverse and function gives you that identity x. And next important one is reverse. A raised to x, instead of x you have log x to the base a. This is a raised to x, but in x you have log function like this. For example, 2 raised to log x to the base 2. So base of exponential and base of log should be equal. Then the answer is identity. Identity means x itself. So if I have 2 raised to log x to the base 2, it would be x, remember. It will be next, if I have 3 raised to log 7 to the base 3, then the answer, this 2 will goes away. Like it's like f OF inverse. The answer will be 7 only, this one. The next, if I have 10 raised to log, for example, I have x to the base 10, the answer will be x only. X, composition of exponential and its inverse. Suppose if I have e raised to log x to the base e, then the answer will be that x itself. Right? We use this. Okay, so these are the properties of logarithmic function. I just want to show you graph of log function and exponential function. For detail you can just refer the textbook. If I simply show the graph of fx equals to 2 raised to x, this is exponential function. Roughly, if I show it, you know how to draw the graph. Put x equals to 0, so 2 raised to 0, 1, 0 comma 1 here. If I put 1 here, 1 then 2, so here. If I put 2 here, 2 then 4 here, like this. If I put minus 1, 2 raised to minus 1, 1 by 2, and so on. So this way it has a graph, remember. It's continuous graph. We already noted that the exponential and logarithmic are always continuous. So there is no break in this graph of the function. It passes through 0 comma 1. X is 0, then y is 1, remember. This is a graph of fx equals to 2 raised to x. And now if I draw the graph of log function here, so for example fx equals to log x to the base 2, same I'm taking, you can take 2, 3, anything, remember. If I put 1 here, then you know it is 0, so 1, 0 here, and the other values would be by doing exponential you can do, but it would be like this, remember, it passes through 1, 0, it's like this. This is the graph of log function fx equals to, this is the inverse of this actually, log x to the base 2, it passes through 1, 0. The value here of the log function you see is negative between 0 and 1 here, and this is also an increasing function and without break, so this is also in fact the continuous function. This is just the mirror image of this. If you put the mirror here, you will get exactly this. There are number of graphs you will find in the textbook. This is just for your information. So now discussing exponential and logarithmic function, let's go to next exercise, which is about these two functions. So we know this, let's recall d by dx of a raised to x, already stated exponential function, you know it is a raised to x into log a to the base e. One is this. For example, what is derivative of 2 raised to x? That is 2 raised to x into log 2 to the base e, like this. So one is this exponential function, the other one d by dx of e raised to x. What is that? E raised to x log e to the base e, which is 1, so e raised to x. So derivative of exponentially, that's self, remember. It is e raised to x to the, so here e raised to x into log e to the base e, but you know this is 1, so it is just e raised to x. So derivative of e raised to x is e raised to x. And one more thing which we have noted, that is derivative of log x to the base e. Remember, base is always e when you differentiate it. Then it is 1 upon x. And here x domain, you know, any positive real number. So derivative of log x to the base e is 1 upon x. Now, for example, if I have like this, differentiate, find the derivative of log x to the base 10, you cannot write directly 1 upon x, remember. Derivative of log x to the base 10 is not 1 upon x, base e is 1 upon x. So what is the first step? You change the base, you know, change of base rule. What is that? You know, it is division of log, this variable x goes to numerator, this goes to denominator, and new base. Which base you want? Base e. Whenever you differentiate, you require base e, remember. This is change of base. Now this is a constant. You see there is no variable involved in this. So I'll keep 1 upon log 10 to the base e as it is. No need to use division rule, and this is simply log x. What is the derivative of log x? You know, 1 upon x. If you want, you can write one more step. If you take a reciprocal of log function, this base and number get interchanged. So e to the base 10 into 1 upon x. This is final derivative. So this should be clear to you. Remember, derivative of log x to the base 10 is not simply 1 upon x. It is log e to the base 10. No need to put the value of this. You can keep in this form. One more, if I take, suppose I want to get the derivative of log, let me write x to the base 2. Can we write 1 upon x? No, I need to change the base. So d by dx, how do I change the base? Log x will be in the numerator, log 2 in the denominator, and the new base, which is base e. Remember, now we can differentiate. This is constant. I'll take it outside and I'll take in the numerator. So it will be e to the base 2, reciprocal. What is derivative of log x? It is 1 upon x now. No need to use division rule. Question is here one more. Suppose if I have this, then what is your answer? D by dx of log, let me write, for example, 2 to the base e. Then what is the derivative? 1 upon 2? No, it is 0, remember. Because you see, this is purely constant. Your derivative is not 1 upon 2, remember. This is wrong. Here it is 0. There is no variable x. This is purely constant. Log 2 to the base e. Derivative is 0. Log x, this is a variable. Derivative of log x is 1 upon x. Okay, so with this knowledge, now let me go to next exercise 5.4, first question. Differentiate following functions with respect to x. The first question, you are given e raised to x upon sine x. So I'll start with, in the solution, d by dx. So in the solution, d by dx of e raised to x upon sine x. How do we do? Division rule. So square the denominator function, sine square, sine x as it is, d by dx of e raised to x minus, interchange this to e raised to x as it is, d by dx of sine x. So sine x into e raised to x minus e raised to x into derivative of sine, which is cos x, you know, upon sine square. This is your answer. If you want, you can take e raised to x common. So sine x minus cos x upon sine square. Question number 2. The function is e raised to sine inverse x. So you need to use chain rule. Let me call this as fx, for example. Fx equals to e raised to sine x, sine inverse x. Chain rule, you don't have derivative e raised to sine inverse x. So I'll imagine this as x. So f dash x equals to, if this is x, what's the derivative of e raised to x? E raised to x into, by chain rule, d by dx of sine inverse x. So we get here e raised to sine inverse x into 1 upon root of 1 minus x squared. So this is the answer. Third question, question number 3. There you are given e raised to x cube. So d by dx of e raised to x cube. You imagine this is like x. So here e raised to x into d by dx of x cube, like the previous question. So e raised to x cube into derivative of this, which is 3x square. Okay, next question, question number 4. You are given sine of tan inverse of ex. You must have realized there are 3 functions, sine, tan inverse, and e raised to x. So we need to use chain rule twice. So let me start with this, d by dx of this. So you know sine x, cos, derivative of sine x is cos x. So I'll imagine this as x. So this is cos of tan inverse e raised to x into d by dx of tan inverse of e raised to x. Now in the next step here, this is equals to this one as it is, cosine of tan of e raised to x as it is, into, now imagine this as x. What is derivative of tan inverse x? 1 upon 1 plus e raised to x the whole square. This is x. Derivative of tan inverse x is 1 upon 1 plus x square into d by dx of e raised to x. So final derivative, this one as it is. This is 1 upon 1 plus e raised to 2x into what is derivative of e raised to x? That's e raised to x. This is your answer. Next question, fifth one. Here, question number 5. You are given log of cos of e raised to x. So same way, imagine this as x. So what's the derivative of log x? 1 upon x. So 1 upon cos of e raised to x into now differentiation of this portion. So imagine this as x. So it is minus sine of e raised to x into now derivative of e raised to x, which is e raised to x. So this is, if I call this as fx, then this is f dash x. I wrote it directly. You can write in detail, remember. One more step, if you want to write, this become minus e raised to x as it is, and sine by cos, that become tan of e raised to x into e raised to x. Log of something 1 upon something. So 1 upon cos, then derivative of cos minus sine, and then derivative of e raised to x is e raised to x. Minus sine as it is, sine by cos is tan, e raised to x as it is. Go to question number 7 now. Let's take y equals to root of e raised to root x. Okay. I want derivative, so I'll write dy by dx here. So you know, inside the square root you are going to imagine this as x. Derivative of root x, you know, 1 upon 2 root x, that we know. So here what I'll get, 1 upon 2 entire that root expression, e raised to root x into d by dx of e raised to root x. I repeat, you imagine this as x. So what's the derivative of root x? 1 upon 2 root x, 1 upon 2, you copy that root expression into d by dx of this expression. Okay. So this is 1 upon 2 into e raised to root into, now you imagine this as x. What's the derivative of e raised to x? E raised to x into derivative of root x, which is 1 upon 2 root x. I repeat this. I'll imagine this as x. What's the derivative of e raised to x? E raised to x. By chain rule, derivative of root x, which is 1 upon 2 root x. So your final answer is this one. 2 into 2, which is 4, root of e raised to root x into root x. This is your final dy by dx. That's the derivative of given function here. Next question. So next question is log of log x. Here base is not mentioned. That means we consider as e, remember. So we start with d by dx of log x. I repeat, base you are not given here. That means base is e. We imagine this as x. What's the derivative of log x? 1 upon x. So 1 upon log x into d by dx of that bracket, which is log x. So here 1 upon log x into derivative of log x, which is 1 upon x. So this is your answer. Now next question, that is simply division rule. I'll go to question number 10. That is 10th question. You are given cosine of log x plus e raised to x to the base e, where x greater than 0. So in the solution, let me start with d by dx of cos of log x to the base e. Your base is not written, means base is e, remember. So we use chain rule. We imagine this bracket as x. What's the derivative of cos? You know, minus sign, and that bracket as it is, log x plus e raised to x by chain rule into d by dx of here d by dx of log x plus e raised to x. So this is minus sign log x plus e raised to x as it is into, now differentiation of this. What is derivative of log x? 1 upon x. And what's the derivative of e raised to x? E raised to x. So this is your answer.